All right, it's 2025, October 1st, approximately 12:34 p.m., proceeding with 4.3 exercises. So we start off here with 4.3-1. Use the substitution method. To show that each of the following recurrences which are defined on the reals has the asymptotic solution applied. Solution specified, sorry. So the first of these, t of n is equal to t of n minus 1 plus n, and we're given has solution t of n equal to big O of n squared. So for each of these, let's assume t is non-decreasing, right? And base cases are aborted into constants. Floor and ceiling effects do not change asymptotic, so we don't have to worry about that. Intuitively, unrolling adds n plus open parentheses n minus 1 close parentheses plus ... plus 1, which is equal to theta of n squared to a constant base. Looking at this more rigorously, right? So we'll go through these one at a time. I won't state all of them at once as one big chunk and then go back and forth. We'll just do it this way. Okay, so for the first one, which we want to show, so we have t of n is equal to t of n minus 1 plus n. Has solution, we want to show, has solution t of n is equal to big O of n squared. So what's the rigorous approach to this? Well, let's assume t of 1 is less than or equal to c for some c greater than or equal to 1, and all m less than n, t of m is less than or equal to c m squared. Well, what can we say then? Well, we can then say that t of n is equal to t of n minus 1 plus n, which is in fact less than or equal to c times open parentheses n minus 1 close parentheses squared plus n. And this is equal to c n squared minus 2cn plus c plus n, which is less than or equal to c n squared when n times open parentheses 1 minus 2c close parentheses plus c is less than or equal to 0. Which holds, this holds for all n greater than or equal to n naught, which is equal to the ceiling function c divided by open parentheses c 2c minus 1 close parentheses. So what then can we say? Well, for one thing, well, this is basically pretty much wrapped up. We can say, okay, so t of n then is equal to big O of n squared. All right, now let's proceed to the next part. So for this next part, t of n is equal to t of n divided by 2 plus theta of 1. And we want to say this has solution t of n, which is equal to big O of log n. Okay. So each step halves the size and adds big O of 1. So the depth is theta of log n. But let's look at it more rigorously. So to begin with, let's write t of n is less than or equal to t of n divided by 2 plus d for some d greater than 0. And let's assume t of m is less than or equal to c log m for m less than n. Well, with this setup, we can say then t of n is less than or equal to c log of n divided by 2 plus d. And this is actually equal to c log n minus c plus d less than or equal to c log n. Okay, and this is the case if c is greater than or equal to d. So t of n is equal to big O of log n. All right, let's move on to the next part. So for this next part, we have t of n is equal to 2t of n divided by 2 plus n has solution t of n is equal to theta of n log n. Okay, so intuitively, how would we approach this? Well, at each level, the total non-recursive work is theta of n across big O of log n. So at each level, the total non-recursive work is theta of n across big O of log n. Levels is what I mean to say, n log n. So the same reasoning gives a matching lower bound. So let's look at this a bit more rigorously. Well, let's assume t of n of 1 is less than or equal to c. Now, for the upper bound, let's suppose t of m is less than or equal to cm log m for m being less than n. Well, then t of n is equal to 2t of n divided by 2 plus n. And this is less than or equal to 2 times, open parentheses, c n divided by 2 log of n divided by 2 plus n, right? So, and this would be equal to what? It would be equal to cn, open parentheses, log n minus 1, close parentheses, plus n. All right? And there's more to be said on this. Let me just erase this. And this would be, this in fact would be, how do I say this? Well, let's see. This would be less than or equal to cn log n if c is greater than or equal to 1. Now, for the lower bound, which is, we need because we're talking about theta here. So for the lower bound, suppose t of m is greater than or equal to c prime, well, actually, sorry. C prime m log m for m less than n. Yeah, so, the reason why I'm putting that way is because we're looking at c from a different perspective in the case of the lower bound. So, but what could we say then with this setup? T of n is greater than or equal to 2 times c prime times, 2 times open parentheses c prime times n over 2 times log n over 2 close parentheses plus n, which is equal to c prime times n times open parentheses log n minus 1 close parentheses plus n, which is greater than or equal to c prime n log n. And if, it's equal to that if it's greater than or equal to that if 0 is less than c prime, which is less than or equal to 1. So Tn is equal to theta of n log n. All right, now let's move on to the next part. So for this next part, so for this next part, T of n is equal to 2t of n divided by 2 plus 17 plus n has solution. T of n is equal to theta of n log n. So, something to be said about the constant there, but the plus 17 in this case, the shift inside the argument is a constant offset in size. We can absorb it by a change of variables to recover exactly what we found in C, right? So it's exactly that. Now, to put this in more rigorous terms, let's define S of n to be equal to T of n plus 34, right? Then we can say, okay, S of n is equal to T of n plus 34, which is equal to 2t of n plus 34 over 2 plus 17 plus open parentheses n plus 34 close parentheses, which is equal to 2t of n over 2 plus 34 plus n plus 34, which is equal to 2 times s of n divided by 2 plus n plus 34. Right? Now, because of the work that we did in parts, well, I say part C, but I'm labeling them as 1, 2, 3, 4, right? So part 3, we can say, okay, as in the third part, by the same substitution proof with an additive constant, we obtain that S of n is equal to big O of n log n. So T of n is equal to big O of n log n. Okay. Now let's move on to part E. Part 5. It's funny because in my solutions for the notes I wrote them in terms of A, B, C, and, letters, but whenever I typed up the exercise, I put them in like numbered format, I guess because it was easier. I just sort of missed that. But for part 5, we have T of n is equal to 2T of n divided by 3 plus theta of n has solution. So we know that this is going to require upper and lower bounds. T of n is equal to theta of n. All right, okay, so what can we say about this? So here, the non-recursive work, theta of n dominates the branching factor 2 on thirds, since n to the log base 3 of 2 is equal to n to the 0.63 on and on and on is smaller than n. The total should be linear. But let's go ahead and look at this a bit more rigorously. So let's let T of n be less than or equal to 2T of n divided by 3 plus Cn for a constant. Or a constant, if I didn't do this before, that's my mistake, for C greater than 0. Let's assume T of m is less than or equal to dm for m less than n. Then T of n is greater than or equal to, open parentheses, 2e over 3 plus c prime. Oops, no, 2d, sorry. 2d, I'm getting ahead of myself, but, so we have this d business. Let me think about this. Oh, okay. Here's what I got. So T of n is actually less than 2d times n over 3 plus cn, which is equal to, open parentheses, 2d over 3 plus c, close parentheses, times n, which is less than or equal to dn, if d is greater than or equal to 3c. Okay. Now let's see what we can do for the lower bound. Now for the lower bound, if T of n is greater than or equal to 2T of n divided by 3 plus C prime times n, with C prime being greater than 0, and T of m being greater than or equal to em for m being less than n, well, what can we say then? Well, we can say then T of n is greater than or equal to, open parentheses, 2e over 3 plus C prime, close parentheses, times n, which is greater than or equal to en, when we have that e divided by 3 is in fact less than or equal to C prime. So T of n is equal to theta of n. And that's it for part 5. Now let's move on to part 6. So for part 6, we're asked, okay, no, we have, for part 6, we have t of n is equal to 4t of n divided by 2 plus theta of n has solution t of n, which is equal to theta of n squared. Okay? So for this one, well, for half-size subproblems, those already cost n squared. The extra plus theta of n has lower order, so let's work with that. Let's approach this as such. So for the upper bound, with t of n less than or equal to 4t of n divided by 2 plus cn, and let's hypothesize that t of m, supposing, right, same thing, is less than or equal to dm squared for m less than n. Well, what we have then is that t of n is less than or equal to 4d multiplied by, open parentheses, n over 2, close parentheses, squared plus cn, which is equal to dn squared plus cn, which is less than or equal to, open parentheses, d plus c, close parentheses, n squared. Now, here's an interesting thing, you know, because of the fact that we're working with asymptotics, is that asymptotes, I mean to say, we can say, okay, choosing d large enough gives t of n is less than or equal to d, big D in this case, n squared for some constant d. We can say, okay, for the lower bound case, and that's pretty much it for the upper bound case, right? Now for the lower bound case, with t of n being greater than or equal to 4t of n divided by 2 plus c prime n, and t of m being greater than or equal to em squared for m less than n, we have t of n is greater than or equal to 4e times, open parentheses, n divided by 2 squared plus c prime n, which is equal to en squared plus c prime n, and this is greater than or equal to en squared. So we have our upper bound and we have our lower bound, so t of n is equal to theta of n squared. There, concluding part 5, well, part 6, in completing the first exercise. Let's move on to exercise 4.3-2. So for 4.3-2, we have that, let me see, the solution, we have the solution to the recurrence t of n is equal to 4t of n divided by 2 plus n turns out to be t of n is equal to theta of n squared. We're told show that a substitution proof with the assumption T of n is less than or equal to Cn squared fails. We're then told, then show how to subtract a lower order term to make a substitution proof work. All right. So intuitively, plugging T of n less than or equal to Cn squared into the recurrence reproduces the Cn squared plus a leftover plus n, which cannot be absorbed by the same quadratic bound. Strengthening the, okay, so we can strengthen the induction by subtracting a linear slack. So prove T of n is less than or equal to Cn squared minus d, n for some constant d greater than 0. The extra minus d sub n cancels the stray plus n after the recursive step. So let's go ahead and carry out that approach in a rigorous fashion. A more rigorous fashion. So we want to show why, first of all, we want to show why T of n less than or equal to Cn squared fails. So let's assume the inductive hypothesis that T of m is less than or equal to Cm squared for all m less than n. Well, then T of n is equal to 4T of n divided by 2 plus n, which is less than or equal to 4 times C times, open parentheses, n divided by 2 squared plus n, which is equal to Cn squared plus n, which is in fact greater than Cn squared for every n greater than 0. So what can we say? So the bound T of n less than or equal to Cn squared cannot be proved by simple induction, sorry. Okay, so we're going to have to shift some things around, which is what I got to in the intuition, which is what I was mentioning, intuitively speaking. So let's show that something does work, more rigorously speaking, right? So let me get to that. So let's create a strengthened hypothesis. So let's strengthen, well, let's go about this. Strengthened hypothesis with a subtractive term. So we prove by induction. We aim to prove by induction that, well, for all, I'm just gonna, this is sort of a hand-wavy thing, sufficiently large n, right? I mean, but you can sort of get what I mean whenever I say sufficiently large n, as n approaches infinity, that sort of thing. But that T of n is less than or equal to Cn squared minus dn. Okay, for suitable constants. I keep forgetting that, but yeah, C and d greater than 0. So what's our inductive step? Well, for the inductive step, let me get that. Assume t of m is less than or equal to cm squared minus dm for all m less than n. Well, what do we say then? T of n is equal to 4t of n divided by 2 plus n. Now, this is less than or equal to 4 of open parentheses c times open parentheses n divided by 2 close parentheses squared minus, lo and behold, d times n over 2 close parentheses plus n, which is equal to cn squared minus 2dn plus n. All right. So now, to reach t of n less than or equal to cn squared minus dn, it suffices that negative dn plus n is less than or equal to negative dn. And this is the case if and only if open parentheses 1 minus d close parentheses n is less than or equal to 0. And this actually holds for every n greater than 0, provided we choose d to be greater than or equal to 1. Okay? So let's suppose, okay, let's have a bit of a base case set up here. So let's pick d is equal to 1. And choose C large enough that the inequality holds. It's just a fun thing you can sort of do with these. It's like, it's defining these things it's essential, but it's not as like strict in the sense that real analysis is, because that's, but at least introductory analysis. But pick d is equal to 1 and choose C large enough that the inequality holds for finitely many small n. That is, let's ensure t of 1 is less than or equal to c minus 1, and t of 2 is less than or equal to 4c minus 2. Now, such a c does exist. See, this is how we get to it. Such a c exists because t of 1 and t of 2 are constants. Okay? Therefore, t of n is less than or equal to cn squared minus n for all n greater than or equal to n naught. Now, this implies t of n is equal to big O of n squared. Now, a matching lower bound t of n is equal to big omega of n squared emerges, for example, by noting that with s of n equal to t of n over n squared, the recurrence yields s of n, which is equal to s of n over 2 plus 1 over n. All right, so what can we then say? We can then say that s of n is greater than or equal to s of 1 plus the summation from I is equal to 0 to the floor function of log n minus 1 of 2 to the negative I. And that is in fact greater than or equal to s of 1 plus 1. So t of n is in fact equal to theta of n squared. Thus completing 4.3-2. So with our change in the substitution proof. So let's go ahead and move on to 4.3-3. See what we can make out of that. So for 4.3-3, we have the recurrence t of n is equal to 2t times open parentheses n minus 1 close parentheses plus 1 has the solution. So it's similar to the first one. I mean these are all similar because they're from the same section, but bear with me. Has solution t of n is equal to big O of 2 to the n. Now we have show that a substitution proof fails with the assumption t of n is less than or equal to c times 2 to the n, with c being greater than 0, constant. And then we have show how to subtract a lower order term to make a substitution proof work. So yeah, it's very much like the previous one, which is good. Okay, now let's think about this. Okay, so intuitively it's like, well, each step roughly doubles the previous value, right? So 2 to the n growth is natural, but a direct induction with t of n being less than or equal to c times 2 of n leaves a stray plus 1 that cannot be absorbed. So we could strengthen the hypothesis by subtracting a constant slack like we did in the previous one, and say, okay, let's prove t of n is less than or equal to c times 2 to the n minus d for some d greater than 0, right? So that constant cancels the leftover plus 1 after the recursive step. Now let's try and show that a bit more rigorously here. So the naive bound, which I mean, they're both kind of naive, but the naive bound t of n less than or equal to c 2 to the n fails, and we want to show that, right? So let's assume Wait. Are we given that it fails? Do we have to show that? Yes, we do. Okay. So let's assume as induction hypothesis that T of m is less than or equal to c times 2 to the m for all m less than n. Well, then T of n is equal to 2t of n minus 1 plus 1, which is less than or equal to 2 times c times 2 to the n minus 1 plus 1, which is equal to c times 2 to the n plus 1, which is in fact greater than c times 2 to the n, of course. So what could we then say? Well, we can then say, so the inequality cannot be, it's too terrible. It's forbidden, no. So the inequality cannot be closed with the same C. All right. So let's go on to talking about what we were saying initially, which is strengthening the hypothesis with that additional term, which is subtractive. So it's an additional term which is subtractive, which is a funny way of saying things. So let me just write this. Strengthened hypothesis with a subtractive term so we prove for all sufficiently large n as usual that T of n is less than or equal to c times 2 to the n minus d for suitable constants c comma d greater than 0. Now for our inductive step, sort of abstracted out from the base case, which we will go into as well. Well, no, not from, but just in like to like problem, same problem. Assume T of m is less than or equal to c times 2 to the m minus d for all m less than n. Well, then T of n is equal to 2t of n minus 1 plus 1, which is less than or equal to 2 open parentheses c times 2 to the n minus 1 minus d close parentheses plus 1. And this is actually equal to c times 2 to the n minus 2d plus 1. And that is actually less than or equal to c times 2 to the n minus d, provided d is less than or equal to 1. So now let's look at a base case and try to see this a bit more concretely. So for the base case, which is just interesting because it's like it's sort of a mesh of things. But for the base case, let's choose d is equal to 1, and let's take c large enough that t of 1 is less than or equal to c2 minus 1. And similarly, let's say for finitely many small n, if desired. So what can we say? Well, such C does exist because t of 1 is a constant. So, well, therefore, t of n is less than or equal to c times 2 to the n minus 1 for all n greater than or equal to n naught. So, t of n is equal to big O of 2 to the n. And there's something to be said, so I'll just put this as a parenthetical. So a matching lower bound does exist. Matching lower bound t of n, which is equal to big omega of 2 to the n, follows by a similar inductive argument. So t of n is actually equal to theta of 2 to the n, but that's not what we were asked to show. We were asked to show that t of n is equal to big O of 2 to the n, which is indeed what we have done, and that concludes exercise 4.3-3, and that concludes all of the 4.3 exercises, and we are good to go. Oops, forgot to turn this off.